space and find who is connected to whom and who is disconnected, you might get wrong answers because you might start in one basin of attraction or another basin of attraction, and you'll get, they might both look chaotic and turbulent, but they'll give you different averages. So it's all that other thinking is required. But this is just uncomputable way to do average. And here is a simple idea. And it says, let me look at e to the b times my observable a of, and average that over the space. So all I'm doing, I'm saying, instead of having this integral here, I'll put it up in the exponent. So that's an okay quantity. Now, the real reason why we do this is some a helpful number of no physical meaning. Sometimes you call it inverse temperature, etc. But so this will be some parameter which we'll use in our manipulation, then get rid of it. Why do we do this? We do this because A is additive in time, because A is an integral. So I can split it in little segments as I go on a trajectory. I can add up these trajectory segments, etc. If I have something that's additive, that if I put it up in the exponent, it'll give me something that's multiplicative. And that we need to use our fancy transfer operators. We need something that will be multiplicative. So that's the idea. And what's beta? You can, for example, get t down by taking derivative with respect to this parameter beta, and then set beta equal to 0. So this we do always in statistical mechanics. So we can use this as a function that generates expectation value of A and all of its power, all its moments. But this object is more natural than having it downstairs like we have it here, because this is 8. And Chris, it's for this reason I didn't put 1 over t in there, because then I would have to stick a t here, etc. So it makes it inconvenient. So I define it to be proportional to time and absorb time into this definition, just for convenience. So now, do we know something about behavior of this quantity as time grows? So usually our observable is a reasonable thing. So in our state space, it has some value, it fluctuates, but it doesn't go off to infinity, because that would be not a very useful observable. So I would design another observable to measure something that's getting singular. So usually this has some finite range. So that means when you look at this object, you can actually produce an upper bound on it, because you can, for example, replace it by maximum, supremum, on the trajectory, and then it will be proportional to the time times supremum. So now when you look at this, it means that you can maximize. What you have is, you have an average of start here, start there, because space means I start every place in a space, and then I compute my average. And now on every trajectory, I have exponential growth this time, and I have an upper bound to it. So I know that average over exponentials, all growing exponentially this time, will have to be an exponential. It won't be anything much worse or much better. I can always produce a bound, so it's an exponential. So what I expect is that this object, as time goes large, will have some number, which won't be important to us, and then it'll be growing exponentially with time, and with some coefficient that at the moment we don't know. But the coefficient will depend on beta, because if beta is 0, then I'll be just averaging over 1. If beta is 7, then I'll get more weights, etc. So I'll get different weights. So we expect exponential growth. And this I'll establish more explicitly by the time we construct trace formulas, but this is the spirit. So what we can expect when we're looking at expectation values, we can expect to get asymptotically some exponential behavior, which means in this formula that if I look at expectation value of A, which is the limit, t goes to infinity, 1 over t, expectation value of a t, but that object is derivative with respect to beta. So when I take a derivative with respect to beta, I'll get, for this object, I'll get t times ds beta ds. Are you with me? I'm just putting this asymptotic behavior in here. So now when I take a derivative, it's not just linear in beta, but it's a function, so I bring it down. And then I set beta equal to 0, so this just becomes 1. And I find out that this time cancels, portion to time. And I find out that the expectation value of A is actually just the derivative of this exponential behavior, t beta, evaluated at 0.